That's your new goal. That's a good goal. All right, fundamental theorem of algebra. In algebra 2, like you build up to this like all year, but the fundamental theorem of algebra to me is a big letdown because I felt like it should be some big. Corey, you okay over there? Okay, I know you're super excited about your thing today. But the fundamental theorem of algebra just says a polynomial function of degree n has n complex zeros. Some may be repeated zeros. And to me, I was very disappointed that that was the fundamental theorem of algebra because I felt like it should be something a lot bigger. But so if you have a fifth degree polynomial, you have to have 5 solutions. Some are real, some are imaginary. Right? That doesn't necessarily mean it touches the x-axis 5 times because imaginary zeros don't touch the x-axis or complex zeros. It could be like a multiplicity. You could have an x to the 5th, x to the 4th. It only touches the x-axis 1 time because it might have a big multiplicity there, right? Do you have any memory of this from last year? Did Mr. McClure like play music when you learned the fundamental theorem of algebra? No, it's like a big deal, like horns should sound. We have a fundamental theorem of calculus, which I feel like is much bigger. Like it's more important than this.
How long do we review?
A lot of this semester. Like next chapter 3 is logarithms, which you did last year as well. And really, I think that we might do like a systems of equations if we can fit it in before the semester, but really we might just finish chapter 2, that's a test. Chapter 3 is 2 tests, and that might be all we do this semester. And then next semester is all trig, so that's when all the fun begins. So, oh, but somewhere in this chapter, I forget, maybe at the end of chapter 2, we do proof by induction. That's exciting too. That's new. Ah! All right, here's something kind of new. It's a cool new way to prove. You start every proof with, let's assume an n equals 1 is true.
Okay, can you try to explain something?
Not if it's about proofs.
No, it's not. I don't understand how we can have non-real numbers that are real.
I know. We just call them complex numbers, and I think the fact that we call them imaginary is the problem that we have because we all think about imaginary friends and how they don't really exist. But we just mean like complex, meaning they don't fit in the real number system. But because they have the real number system, we call it the non-real number system. But in terms of math, it doesn't mean like they're like invisible. It just means they don't exist with the same rules that real numbers exist. I had a student that used to call them invisible numbers. Are them those invisible numbers? That's my impersonation of the. A long time ago, you don't know the person.
Hey, Arnold?
No.
Yeah, I can see that.
Before Shay Arnold, okay, so here's something that you didn't really talk about, I don't think, in Algebra 2, but it should make sense, that if f of x is a polynomial of degree n, then you could write it as n factors, right? Because we know that it has n zeros, or n solutions. But the cool thing is we can even do this with imaginary numbers. So here's how they write it. And I know you guys don't like all these letters, but I like to force them on you and say, it's good to see math written like this. Oh my gosh. Pretend that C1 and C2 and C sub n are just any complex number. Right? Think about that one on the test yesterday that lots of people wrote out as zeros, but I wanted them as factors. Right? If there's a 0 at 1, how could you write that factor? X minus 1, right? And so that's all this is saying, that if these are your solutions, or your zeros, wouldn't it be great if my smart board doesn't work today? Oh, there it goes. Just a little slow. We had a cap test today, so it's my first try with it. So if these are your solutions, then you can just write them as factors. And I feel like we know that, we just haven't really written it out. And we usually, in Algebra 2, we never did that with imaginary numbers, but we're going to do that with some real ugly answers today. It's so exciting. So on your homework, it's going to say, write a linear factorization, and that just means write out as linear factors.
Yeah.
Did everybody write this down already? Keep it writing. We've lost too much time.
We don't really even have time.
Yes, we do.
Guess where I did not go to.
Right.
I'm done already.
I know you had a field trip, remember?
Yeah. So I didn't have to go to any.
Wait, what field trip did you have?
So go to a factory.
I didn't when this course.
All right, last writing thing before we have to do some problems. Conjugate pairs. We've talked about conjugates before, like how we get rid of imaginary numbers, how we get rid of radical numbers. And just remember that if you're talking about zeros, you can never have just one imaginary zero. They always come in pairs because you have to be able to get them to cancel each other out. So it says, let f of x be a polynomial function that has real coefficients. If a plus bi is a zero, then its conjugate, a minus bi, also has to be a zero. And imaginary numbers never are alone. They always have a conjugate to go with them. And think about the only way you get imaginary numbers is by completing the square or doing the quadratic formula when you take the square root of both sides, so you always get plus or minus. So you can always think about that, but that's why they come in pairs. But this means now on this next test that we have, I can make you write an equation with certain zeros, one of them being an imaginary zero, and I can test to see if you remember, oh, if one imaginary number is there, then its conjugate is also there. So let me go ahead and show you this one, and then we'll work it out. Because that's just like the very last question on your last test, except for now this one has an imaginary number. And so it says find a polynomial with the given zeros. The only difference in this is it says -2, 3, and 2i. If 2i is a zero, what else has to be a zero? If positive 2i is a zero, then we can say also negative 2i is a zero. And so that's definitely going to show up on that next test question just like this. And then the fun part, just like on the other one, we have to write these as factors and then multiply them out. So if -2 is a zero, what's the factor? X plus 2, right? We just change the sign. And if 3 is a zero, x minus 3. And then with the i's, we're going to do the same thing. Just like with the radicals we did last chapter, I could write that as an x minus 2i and x plus 2i. So we just need to work it out, but here's my advice to you. Multiply the conjugates together, because otherwise, like if you try to multiply x minus 3 and x minus 2i, you're going to get all these i's carrying over. But the great thing about conjugates is when you multiply them together, the imaginary part goes away, right? So when I do these, especially if there's 4 of these, I'm going to FOIL these two together and FOIL these two together, and then I'll FOIL that all together at the end. I squared equals what? Negative 1. Yeah, so when you have I squared, it is a real number. That's why we like imaginary numbers so much. If I FOIL this one out, I'm going to get what? X squared minus 3x plus 2x would be minus x minus 6. We're still a little slow today. And then remember, these are conjugates, so the middle part cancels out, so I don't even usually write that unless you just really want me to. But x times x is x squared, and plus 2ix minus 2ix is going to cancel out. And when I take negative 2i times negative 2i, I'm going to get, I'm going to write that over here, I'm going to get negative 4i squared. But because I squared is negative 1, what do I actually get down here? Plus 4. And if you think about it, sometimes people don't even FOIL it because they think about what would the factor have to be in order to get 2i and negative 2i. You'd have to have x squared plus 4, right? Because then you would get x squared equals negative 4 plus or minus 2i. And then the last step is just to FOIL all that out, and that's where you just got to be careful, watch your negative signs. On the last test, there were a few people that made little mistakes there on your multiplying. And don't forget to write either f of x or y equals to show that you're actually writing a polynomial equation. But I'm just going to multiply everything in this times everything over there. So I'm going to get x to the 4th plus 4x squared minus x cubed minus 4x minus 6x squared minus 24. So I'm just going to combine like terms, and I can't help myself but write it in descending order there. So 4x squared minus 6x squared is minus 2x squared minus 4x minus 24. That would be the polynomial that has those 4 zeros. Questions about doing that? Not so bad to do. Just don't forget, like the big thing that happens is people forget to put its conjugate there, and then you get an answer with i's in it. Your polynomial will never have i's in the worked out thing. So if you get that, hopefully you'll remember, oh, there should be another I to go with that. Okay. The other thing I want to focus on today is actually finding all the zeros. Oh wait, I got one more before we do that. This is also on your homework, and I just wanted to do an example of this because sometimes the directions throw people off a little bit. And especially since you're on a filter tomorrow, I feel like there's going to be quite a few of you that don't even look at this today. Wait till tomorrow night. Maybe you should, because then you might forget. Thursday night you might be like, oh, I have a filter, I have no homework. So maybe you should just do it today. Alright, Mason.
When's it gonna snow?
Friday.
This is due on Friday.
Because you're not going to be here tomorrow, right? You're going to have a filter tomorrow.
I thought it was due on test days.
Maybe I'm going to give you a homework quiz on Friday just to see if you did it.
No, you won't.
I'm going to, just
Do
for
it.
So Mason's gonna have us do it.
Yeah, that's it.
Write the polynomial in standard form and identify the zeros and the x-intercepts. Zeros and x-intercepts, those seem like they're the same thing, right?
But it's like imaginary that it's not actually x-intercept.
Right. It's a solution, but it's not going to actually cross the x-axis. And so when it says identify the zeros and the x-intercepts, can you do that right now?
Yeah.
It's already factored, right? If I wanted to solve this, could I say my solutions are x equals 3i and x equals negative 3i? Or x equals plus or minus 3i? Are you with me today? Did you write that down already? I was kind of distracted yelling Mason. Not yelling, but
So
trying to motivate.
those are the zeros.
yeah, so these are the zeros,
And there's no x-intercepts.
and we would say there are no x-intercepts because complex numbers do not show up on the graph. It also says write in standard form. You know what that means to do? Yeah, it just means multiply it out, kind of like the last one. Like, give me a polynomial all multiplied out, and when it's just conjugates, it's probably not that bad to do. Nothing like the last one with all 4 things. So the only other thing I'm going to do on this is I'm going to FOIL that out and get x squared. The middle term drops out, and that's going to be minus 9i squared. Or that's just x squared plus 9. If you think about when you graph that, what's that going to look like when you graph it if it's just x squared plus 9? It's gonna, yeah, it's just going to be moved up 9, and so that's why it has no x-intercepts, because it doesn't ever touch the x-axis. Okay, so I just want to make sure we talk about the difference between zeros. Zeros are like solutions, but the x-intercepts are if it actually crosses. It has to be a real number to cross that. Okay, the other thing we're going to do today is actually find all the zeros, just like you did on your test when it said find all the real zeros. The only difference is we're going to include the imaginary ones now, which means no matter what, you have to divide it out and do the square root of the quadratic formula. Before we do that, there's one more rule that you learned about last year that we haven't talked about, which was Descartes' rule of signs. I'm going to show you that. It's very wordy, so it's up to you if you want to write it all out. I'm fine. I'll wait for you to write it out. Or if you want to just wait and we'll do an example, I'm okay with that too. But I just want to show it to you because I think you'll remember once we talk about it. But there's really not a short way. Descartes, here's my lovely picture of Descartes. Rene Descartes. He didn't have a good way of shortening this up. But he came up with an idea of how you can figure out how many possible positive real zeros, negative real zeros, and complex zeros exist by just looking at the sign change. So I'll be quiet a minute for those of you that want to write it down, and let you write it down, and then we'll talk about it and we'll actually do one. There's no place. Okay, I'm going to keep talking for just 1 second. Last year in Algebra 2, there are certain places on the test for this chapter that you did in Algebra 2 that you had to use Descartes' rule of signs. I'm not going to make you use Descartes' rule of signs. It's just a way to kind of help. If you know there are no positive real zeros, then you don't have to check any of your positive PRZs. Like, that's where it's kind of useful. But sometimes have part. There's a part number 2 to this, right? Let me just go ahead and show you number 2 also before we move on. I know, it's the worst part of the lesson, I think. Well, there's a big problem. There's only 2 more examples, though.
So if I wanted to create a math wall, what
Yes.
would I have to do that?
There's a lot you have to do.
Because
Well,
I got something in my head. I can't say it because I know you guys will try to steal it.
Every theorem or rule that's in math has to be proven. So if you have something, first of all, you have to see if anyone else has already come up with it. Because if it has, then you don't even need to waste your time. But if it's something new, then you have to develop this theorem, and then you have to come up with proof with it. And then I don't even know what you would do with it. Submit it to some math journal and let other people see if they agree or disagree. But like Fibonacci has his own little rule. And then what's the someone's last theorem? There's some guy that died, Fermat. Fermat's last theorem? Yeah, he died before you could prove his theorem, whether it was true or not. And then like people spent like years trying to prove it to see, because like you can check every number. Like you can keep saying, I'll check this number, it works. I'll check this number, this works. But that doesn't work in math. You have to prove it that it would work for like any n number. And so Fermat died before you could prove his last theorem. And then like just in like the 1980s, someone, or maybe even after that, someone proved it. And there's a whole book about it.
It's my theorem that I've come up with. It's so simple. Like,
just say it, Aaron. Nobody's gonna take it.
You'll say it later. Let's do this first. So if you have a polynomial function, you can tell the possible number positive real zeros because it's either going to be equal to the number of variations in sign or less than that by some even number. This is where like we would take it, we're going to do one in a minute, but like you look at the sign changes, you're like plus, plus, minus, plus, right? And you count how many times does it change sign. It changes sign here, 1, it changes sign here, 2, so we say like 2 or 0 positive real numbers. Do you have any vague memories of that? And like if there were 6 sign changes, you go like 6 or 4 or 2 or 0. Alright, we'll do one of them. Good job during the week. Always goes down by an even number. Yes. And so the number of negative real zeros is also equal to the number of sign changes, but you have to plug in negative x or less than that by a real number. So if there were 3 sign changes, there could be 3 or 1, because you always subtract by 2. And then once you can't subtract 2 anymore and it would be negative, then you're done. So we'll do this on one of them, and like I said, it's sometimes helpful, but it doesn't actually give you the number. Like it says like 2 or 0. How do you know if there's 2 or 0? You actually have to find them still. So that's why it's kind of nice sometimes, but other times it's just like, why did I waste my time? Because it didn't help me. So that's why I say it's kind of up to you if you do it or not. But I'll show you on this next. All right, so this one says, state how many complex and real zeros the function has. You would think Descartes' rule signs might help us, but it just gives you a possible number, and then we still have to use PRCs and actually find some of them and figure out what's happening. But notice on this one, they don't actually care what the zeros are. They just want you to say how many are real, how many are imaginary or complex. Yeah. So first of all, how many total zeros does this problem have to have? 3, because whatever the degree is, you have to have that many total solutions, okay? So there's no more like just ignoring the imaginary ones. You have that many total ones. So this is where we could use Descartes' rule signs. So when I do Descartes' rule signs, step 1 is I just look at the function itself, and I just write the signs down. So like that's a positive number, that's a negative number, that's a positive number, and that's a positive number. And I just count how many times did it change sign. 2. It changed positive to negative, and then negative back to positive. So I could say that there are 2 or 0 positive real zeros. So there might be 2, or there might be none. And also notice that it just says real. So don't get that confused with PRZs, right? PRZs are the possible rational zeros. Could a real zero be an irrational number? Yeah, so sometimes people think, oh, that means 2 or none of my PRZs are going to work. None of your PRZs might work because they might be all irrational. So that's, again, where people get confused. For negative real zeros, we plug in negative x. And it's really easy to tell. If you have an odd exponent, is a negative going to change your sign? Yeah, so that's going to change to negative. But if you have an even exponent, is a negative x going to do anything to that? No, so that's going to stay negative. What about x? Is that going to change? Yes, so that's odd. And a constant's never going to change, so that's going to stay positive. So how many times did that change? So I know there is one negative real zero. It might be irrational, but there is one negative. And then last year we said now you can figure out how many possible imaginary ones you could have also, because if we know there are 3 total, if there's 2 positive and 1 negative, how many are left that could be imaginary? Yeah, if there's 2 positive and 1 negative, then there's none left that could be imaginary. But Cora says, well, what if there's 0 positive and 1 negative? Do you agree that there could be 2 possible of 2 imaginary? With me on that? This is kind of, like I said, to help you, not required at all. Like on your homework today, if you don't ever use this, I'm okay with it. But some people really like to get the idea. And you can check your answers that way, because if you end up with 2 imaginary and 1 negative, you're like, oh, I'm right. But if you end up with 2 imaginary and 1 positive, something's wrong, because there can't just be 1 positive. How do you come up with these? You got to do PRZs. So what's great about this problem? What would my PRZs of this be? Factors of 1 over factors of, oh my goodness. I only have to check 1 and negative 1. I know, it's my favorite problem.
I'm guessing there's none like that.
If I plug 1 in there, I get 1 minus 3 plus 1 plus 1. Does that equal 0?
Yeah.
1 plus 1 is 3, and 3 minus 3 is 0, which means 1 works. Which means I know there's a 0 at x equals 1. What does that tell me about my zeros now? If 1 is a 0, is my other 0 have to be positive or negative? Because if there's 1 positive, there has to be 2 positive. That's what Descartes' rule of signs tells us. What should I do now? You could check negative 1, but it doesn't work. I don't think it works. But you can check it since there's only 2. But I'm going to do synthetic division, just like hopefully you did on your test. Plug that in. 1, negative 3, 1, 1. We already know it equals 0, so we better get 0 here. I mean, I'm getting ahead of myself. That would be negative 1, 0. So excited about the 0 there. And what should I do with what's left? Yeah, write it out, right? So if this was x cubed, then I'm left with x squared minus 2x minus 1. Is that factorable? So here's the nice thing. Do they actually care what the zeros are up here? They just want to know how many of which kind. Which means I'm going to either complete the square or do the quadratic formula. But as soon as you can figure out whether they're real or imaginary, then you can quit this problem. Does that make sense to what I'm saying?
Well, don't we already know because x.
So x equals 1, so we know that there's 2 here, right? But how do you... Oh, yeah, we do now. I was about to say, how do you know whether it's this or this? Everybody following what Cora's saying? Because we know there's 2 positive, can there be 2 imaginary also? Which means there has to be 1 negative, which means you could just stop this problem right away. I was keep going here. But because they don't actually ask you what the zeros are, you could say, you know, there are 3 real zeros. Does that make sense? We could solve it out, but it's not requiring us to. So sorry, I was making you do extra work. We could have stopped a long time ago. 3 real zeros. 0. Yes, no, maybe? Okay. Let's actually do one that we have to solve all the way out, right? It's my last one. And here's the new part. Not only are we finding all the zeros, including imaginary zeros, but we're also going to write it as a linear factorization, which kind of looks scary at times when you get really ugly answers. So I want to make sure that we do one of these together. Also, how could I make this worse is I gave you an x to the fourth, right? Which means you're going to have to find two PRZs unless it ends up being factored by group B. So do you want to do Descartes' rule of signs or no Descartes' rule of signs? I'm okay now doing it. So that means where should we start if we're trying to find the zeros? PRZs. And again, look how nice the coefficient's 1, which means we don't have to check any fractions. So do you agree we're just going to take factors of 6 for our PRZs because it's over factors of 1? So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And for me, when I see that it's x to the fourth, as soon as I find 1 0, I'm going to divide it out, rewrite it, and see what's left because I know I want to get it down to x squared. I think, does 1 work? You get 1 plus 1 plus 5 minus 1 minus 6. So happy when 1 works. And so I'm just going to divide that out. And it's up to you. I don't know if it was this class or 6th hour that we talked about this, that when you have to do it again, sometimes you don't have to rewrite it as x to the third. Like if you just like think in your head, this is x to the third, x squared, x, and your constant, and you're just trying to check numbers again. Someone asked me, is it okay if I just go again and not actually rewrite it all? I'm okay with that. But I'm also okay if you want to rewrite it as x cubed plus 2x squared plus 7x plus 6. I'm going to just keep going down the line. I'm going to check negative 1. And I get negative 1 plus 2 minus 7 plus 6. On a lucky day, I think it works. So now if I divide again, I'm going to get a quadratic. That's what you have to go to. That's why the biggest one I usually like, I don't think there's any bigger than x to the fourth power, because you have to find 2 PRZs and then you get a quadratic. Once you get a quadratic, you don't have to check anymore because you can do quadratic formula or complete the square. So that would be, again, divided out to 7, 6. So I get x squared plus x plus 6, and now I can solve that. Don't forget to give me all the answers, all right? So we solve this, people give me those answers, but don't forget we already found 2 zeros. So what I like to do is when I write this, I write also right next to it, I already know that x equals plus and minus 1, right? Like I already know there are 2 real zeros to this, so don't forget to give me those answers that you found. And I'm probably just going to do quadratic formula on this. Is that all right? Completing the square is okay. You just have to deal with fractions here. But I'm just going to do negative b, so that's negative 1, plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. See how these problems can take a little bit of time, a little bit of paper. So what is that? 1 minus 24, so that's going to be negative 23 under the radical. So I'm going to go ahead and pull that imaginary part out and say that's I radical 23 over 2. So really this is nothing new from what we just did in the first half of chapter 2, except now we're going to get imaginary answers. That's the only real difference. But they also want you to write this as a linear factorization, which means they want you to write them as factors. For 1 and negative 1, that's not a big deal. But they also want you to write this as a factor, and so people get a little scared with that sometimes.
Keep it the exact same thing as you would with the square.
You should, yes. I believe the square, it probably looks like this. Plus or minus I radical 23. Like, you probably kept it separately. But yes, you should get the exact same thing. Take half. Did you do 1/4 on each side? That's why you should use fractions. Because I'm sure that works out decimals to be the same thing, but it's not going to look so nice. So if you complete the square, fractions, not decimals. Okay? Fractions are our friends. Decimals are not. So here's a linear factorization. I'm going to write this function as all of its factors multiplied out together. So for 1 and -1, could I say that's x minus 1 times x plus 1? You with me on that part? We have to do the same thing for this, and you're still going to do the same thing. You're just going to change the signs as you go. Does that make sense? So do you agree that these are two answers here? It's like -1 plus I radical 23 over 2, and -1 minus I radical 23 over 2. If you subtract that, it changes all the signs. So that's going to be a factor of x minus -1. You agree that's going to change to x plus 1. And if I do the top one first, that plus is going to change to minus I radical 23 over 2. I'm going to erase this so I can put the other one here. Times, oh, that's an eraser. The same thing, I'm going to subtract, so that's still going to change to plus 1, but now it's the minus 1, so that's going to change to plus I radical 23 over 2, parentheses. Sometimes people get scared by the negatives. You could just write it as x minus parentheses -1 plus I radical 23 over 2. Like, if you don't want to deal with switching the negative signs, just put in parentheses. I'm okay with that. But if we multiplied all this out, it should equal the real thing. Are you ever going to have to multiply imaginary roots out like that? No. But that's what a linear factorization is. It takes all the zeros and writes them as factors. That looks like a scary answer, doesn't it? Show that to your friends so they can be scared. This is what math turns into. But you can just impress them that you're doing this awesome stuff. All right, so that's the kind of the new thing, and it kind of just doesn't look so nice. But linear factorization. Questions about that? I don't have a new assignment sheet for you yet, but you just have one assignment, so we'll do that. I'll bring the assignment sheet. But here you go: 2, 5, day 1, 3 through 9 multiples of 3, 17 through 20, 21, 27, and 30. 17 through 20 are matching a graph to an equation. Look at the multiplicity on those. Look at the zeros. We'll talk about